Hello everyone, I am Manish Agrawal and thanks for watching Edupedia World Videos. So the next law that we have to study in this session is Avogadro's law. And we have actually seen Avogadro's hypothesis in some detail in the topic of mole concept before. We have also solved numerical problems based on this. But for now here let's look at it once again very quickly from the perspective of an ideal gas and from the perspective of our gas law. So Avogadro's law basically again has some kind of similarity to the other laws that we have studied, except here instead of number of moles, temperature and pressure are kept constant. Alright, so that means in our equation PV is equal to nRT. Okay, so in this equation here right now we have pressure T, temperature and R gas constant. These three things are constant and volume and number of moles can change. Okay, so in our container which has the gas, okay, the volume that is can change of the container, that is the walls are movable, plus there is an escape nozzle, okay, from where the gas can escape out and new amount of gas can also enter in. Alright, so in such a case it's quite clear that V is equal to N into RT by P. Right. So that means volume is directly proportional to number of moles. So this is what Avogadro's law or Avogadro's hypothesis was, that volume occupied by any ideal gas is directly proportional to number of moles of that ideal gas inside the container. Alright, given that temperature and pressure are kept constant. So one important thing over here, if you remember, is that this number of moles N, okay, these are number of moles of molecules, okay, or in more specific terms it is basically number of moles of standard state of any gas. That is to say, if you take oxygen gas exists in form of O2 and not O. Alright, so here N is number of moles of O2, not O. Alright, similarly if you take nitrogen, here N is number of moles of N2 and not N. Alright, but whereas if you take helium, helium doesn't exist in form of He2, right? That is wrong. Helium is a noble gas, so it exists in atomic form He. So here N will be number of moles of helium atoms. Alright, and this is true for all the noble gases, they exist in atomic form, so here N will represent their moles of atoms. Alright, and if you talk about say ozone gas, then ozone is again made up of oxygen atoms, but its molecular formula or its standard state or stable state is O3. Alright, so that means here N will represent number of moles of molecules of O3 in case of ozone gas. Okay, so that is what N here represents in PV is equal to nRT, and RT and P are constant, so we don't have to worry about it, except that temperature must be taken in Kelvin. Alright, and volume can have different units depending on the value of R, and N always has the unit of mole. Alright, and one thing here, Avogadro's constant, that 1 mole is represented by Na, and it is equal to 6.022 into 10 to the power 23 number of entities. Okay, so let's analyze this Avogadro's law once again in a little bit detail. So the first important thing that we can note over here is that molar volumes are independent of type of gas. Okay, so first, what do I mean by molar volume? Okay, so molar volume means volume of 1 mole. Alright, it is represented by V with a subscript M. Alright, so Vm is the symbol generally used for molar volume. It is basically equal to number of moles divided by N. Okay, so molar volume is independent of type of gas. That means for any given gas, whether it is CO2 or say CH4 or ammonia or oxygen or any gas, alright, for all the gases, as long as we consider them to be ideal gas, their V by N ratio will remain constant under the same condition of temperature and pressure. Right, we can see this in mathematical form from over here. Right, so V is equal to N into RT by P, and this RT by P can be taken as a constant, say K. So this makes it V is equal to K into N, which makes V by N is a constant K, which is equal to RT by P. So as long as P and T are kept constant, or the ratio of T and P is kept constant for different gases, their ratio of volume and moles will always be same. Okay, and this ratio is basically called molar volume. Okay, that is volume occupied by 1 unit of mole or 1 mole of gas. Okay, so that is why we said here that molar volumes are independent of type of gas. The other important thing you must know is about STP and NTP. Okay, so if you remember, what are the conditions at STP and NTP? So at STP, the condition is 273 Kelvin temperature, approximately, exactly it is 273.15, that is 0 degrees centigrade, and pressure is 1 bar. Okay, initially STP was taken as, that is standard temperature and pressure condition was taken as 273 Kelvin and 1 atm, that is 1 atmosphere, but now that has become NTP and STP is 1 bar. So NTP is now 273 Kelvin, that is normal temperature and pressure is considered to be 1 atm and 273 Kelvin. Okay, so this is the difference between STP and NTP. Alright, and if you substitute this value in this equation, V is equal to N RT by P, you can exactly calculate, okay, putting N is equal to 1, that is 1 mole. Okay, you can exactly calculate the volume occupied by an ideal gas under different conditions of temperature and pressure. So it turns out that at STP, volume occupied by all the ideal gases, okay, 1 mole of all the ideal gases is equal to 22.7 liter. That is molar volume at STP is equal to 22.7 liters. Okay, approximately. So in most of the literature, still you find that the molar volume is taken to be 22.4 liter. That is based on old form of STP, okay, or old conditions of STP. In reality, molar volume at NTP is actually equal to 22.4 liter. So you must know this difference. Okay, but also remember that in most of the questions and in most of the theory and literature, you will still find molar volume taken to be 22.4 liter both at STP and NTP. Since there is little difference between 1 bar and 1 atm, it is assumed that STP is approximately same as NTP, and for both we can take molar volume to be 22.4 liter instead of making a difference. But you must also know the difference between them. Okay, apart from these two conditions, we had also studied another condition called SATP, standard ambient temperature and pressure. Okay, so that was 298 Kelvin and 1 bar pressure. Okay, and under those conditions, molar volume of any ideal gas comes out to be approximately 24.8 liter. Okay, so this you might not remember, you can calculate in case there is a requirement of it in a question, but at STP and NTP the values of molar volume must be memorized. You won't have time to solve it, and these values are quite often used in various numerical and even in some theory questions. Okay, so just remember these values by heart. So let's solve a quick question on Avogadro's hypothesis and let's get done with all the gaseous laws. So here we have to find volume occupied by a mixture of 2 mole hydrogen atom and 1 mole oxygen atom at STP. That means they have given us a container containing 2 mole of hydrogen atom. Okay, 2 mole of H, alright, and 1 mole of oxygen atoms. Okay, so do remember that the word used here is atom and not molecule. Okay, but we know that under STP, H doesn't exist in form of H, it actually exists in form of H2. Similarly, O doesn't exist in form of O, it will exist in form of O2. So this means under STP, you will actually have the amount of ideal gas inside will be 1 mole of hydrogen gas. Okay, so 2 mole hydrogen atoms means 1 mole hydrogen molecules, right? This we have done before in mole concept, how to calculate this. Similarly, N2, that is moles of oxygen gas, will be 1 by 2, right? So 1 mole oxygen atom means 1 by 2 mole of oxygen molecules. So total amount of gas present with you, okay, will be simply N1 plus N2, that is 1 plus half or 3 by 2 moles. Okay. So why are we adding the number of moles? Because it doesn't matter which type of gas is present. Okay, that's what Avogadro's law is about, that the volume doesn't depend, in fact the behavior of any ideal gas doesn't actually depend on the type of gas, it only depends on the amount of gas under given temperature and pressure conditions. So we can directly add the number of moles and treat both the gas as one single gas for now, and then calculate the volume. So how do we calculate the volume? We can use simple unitary method, that 1 mole of ideal gas at STP we just saw occupies 22.7 liter. So how much volume will 3 by 2 mole of ideal gas occupy? Let's say V. Okay. So use unitary method, that is to cross multiply. Okay, we get from here that 1 mole multiplied with V is equal to 22.7 liter multiplied with 3 by 2 moles. So from here you can directly solve for the value of V and you will get your answer in liters. Okay, so this is how you can use Avogadro's law to solve your problems. So with this we have finished up all the individual gas laws. Okay, so in the next session we'll directly go to the combined form of gas law and ideal gas equation. Alright, and with that we'll have finished everything related to ideal gas equation or equation of state. Okay, and then we can move on to the other theories in the chapter. Alright, so until next time, and once again thanks for watching Edupedia World videos.